Welcome back to our channel. Today, we're diving into the fundamentals of databases and understanding what data really is. Main headlines. What is a database? Use of database. Types of database. Database languages. SQL, MySQL, PostgreSQL. Brief definition of a database. Data is actual information stored in the database, for example customer names, addresses, product details. A database is an organized collection of data, so that it can be easily accessed and managed. You can organize data into tables, rows, and columns, and index it to make it easier to find relevant information. Databases. A database is an organized collection of data that can be easily accessed, managed, and updated for various applications. Spreadsheet. A spreadsheet is a digital tool that organizes data into rows and columns, allowing you to calculate, analyze, and manage information easily. Databases are much more powerful than spreadsheets due to data query and manipulation capabilities. Retrieve all records that match certain criteria. Cross-reference records between tables. Update records in bulk. Perform complex aggregate calculations. Spreadsheets are flexible and provide more user interface features. Retrieve all records that match certain criteria. Allow any data to be entered into a cell. Convert data into graphs. Format directly into printable reports with a header and a footer. There are two main types of databases, relational and non-relational. Relational databases, or RDBMS, organize data into tables with rows and columns, making it efficient for structured information. Object-oriented databases, or OODB, store data as objects, which allows complex data types and relationships to be represented directly. Now let's look at some other types of databases. NoSQL databases. These are non-relational and handle unstructured or semi-structured data. They became popular as web applications grew more complex. Cloud databases. These run on cloud computing platforms and are offered as a service. Both relational and non-relational databases can be hosted in the cloud. Data warehouses. Think of these as central repositories that store both current and historical data. They're designed for analysis and reporting across the enterprise. Distributed databases. These store files in multiple locations, sometimes on different computers or even across networks, yet they work together as one system. Let's talk about the Relational Database Management System, or RDBMS. An RDBMS stores data in a structured format, using tables with rows and columns. This idea comes from the relational model introduced by E.F. Codd in 1970. The key concept is that data is represented as records in tables, and relationships between those tables are managed through foreign keys. Examples include MySQL, PostgreSQL, Oracle Database, and Microsoft SQL Server. RDBMS is ideal for applications that need structured data, complex relationships, and strong consistency, like financial systems or customer management systems. Let's look at non-relational databases, often called NoSQL, which stands for not only SQL. Unlike relational databases, NoSQL does not rely on tables and rows. Instead, it's designed to handle large-scale, distributed, unstructured, or semi-structured data. It's more flexible, allowing data to be stored in different formats, like key-value pairs, documents, graphs, or wide column stores. Some popular examples are MongoDB, DynamoDB, Cassandra, and Neo4j. NoSQL is best suited for applications that need scalability and flexibility, and can work with eventual consistency, such as social media platforms, big data analytics, and IoT applications. A direct comparison between RDBMS and NoSQL databases. RDBMS stores data in tables with rows and columns, and is optimized for complex queries and relational data retrieval. It supports joins, uses normalization, and is ideal for systems that require strong consistency, like financial applications, CRMs, and ERPs. NoSQL, on the other hand, is built for scalability and real-time performance. It handles unstructured or semi-structured data, and relationships are managed differently, often through embedded documents or application-level joins. It's perfect for real-time apps, social media, big data, and IoT. Take a closer look at the structure of a relational database management system, or RDBMS. In an RDBMS, data is stored in tables, which are made up of rows and columns. A row, also called a record or tuple, represents a single data entry, like one customer or one transaction. A column defines a specific attribute, such as first name, last name, or date of birth. It sets the type of data stored across all rows in that field. For example, in the sample table shown, each row represents a customer, and each column holds a specific detail about them. Understanding this layout is key to working with relational databases effectively. RDBMS database structure. Look at how data is stored in a relational database. In an RDBMS, data is organized into databases, and each database contains tables. Each table is made up of columns and rows. A column defines a specific attribute, like code, name, or continent. A row represents a single record or data entry, such as one country. For example, in the highlighted country table, we see 3 rows: Aruba in North America, Afghanistan in Asia, and a duplicate entry for Afghanistan in Africa. This structure allows us to store and retrieve data efficiently, and also helps us spot issues like duplicate records or data inconsistencies. Break down the 4 main categories of SQL statements used in database operations. We have DDL, Data Definition Language. These commands define and modify the structure of the database. Examples include create, alter, and drop. DCL, Data Control Language. It's used to manage access to data. Common commands are grant and revoke. Then we have DML, Data Manipulation Language. These statements handle the actual data inside the tables. Think select, insert, update, and delete. TCL, Transaction Control Language. These commands manage transactions, like commit, rollback, and save point. Together, these categories help us structure, secure, manipulate, and control data within a database. Let's go over some important query languages used across different types of databases. First, we have SQL, or Structured Query Language. It's the standard language for querying and managing relational databases. SQL is Oracle's extension of SQL, adding procedural programming capabilities. TSQL, or Transact SQL, is Microsoft SQL Server's version, also supporting procedural logic. MySQL is a popular open-source RDBMS that uses SQL. PostgreSQL is another advanced open-source system that supports SQL and procedural languages like PGSQL. Now for NoSQL databases, MQL, or MongoDB Query Language, is used to query and manipulate data in MongoDB. SQL, or Cassandra Query Language, is used with Apache Cassandra. And Gremlin is a graph traversal language used to query graph databases like Apache Tinkerpop. Why we need a database. In the past, data was often stored in flat files or spreadsheets, which lacked organization and structure. As the volume and complexity of data grew, these methods became inefficient. Databases, however, provide an organized structure for storing data that makes it easy to manage, access, and retrieve. Efficient data retrieval, data integrity and accuracy, data security and privacy, support for real-time data processing, scalability to handle growing data, backup and recovery. Entities and relationships. In databases, we work with 2 key concepts: entities and relationships. An entity is simply something in the real world that we want to store information about. For example, in a bank database, we might have a customer table that stores customer details. Each column in that table, like customer name, account number, or contact information, represents attributes of the customer entity. A relationship is the link between entities that are connected. For instance, a customer's name is directly related to their account number and contact information. These relationships allow us to connect data across tables and make the database meaningful. So, entities define what we store, and relationships define how those things are connected. Relation categories. An example: a relationship connects entities that are linked in some way. And these relationships come in 4 types. One-to-one. One entity is linked to one other, like a car and its engine. Many-to-one. Many entities link to one, like many animals in one zoo. One-to-many. One entity connects to many, like one customer with multiple bank accounts. Many-to-many. Many entities connect to many, like students enrolled in multiple courses. Understanding these relationships helps us design databases that reflect real-world connections and support efficient data retrieval. In database design, especially when working with entity relationship diagrams, we use specific symbols to represent data structures. An entity is something we want to store information about, like a student, teacher, or project. In diagrams, entities are shown as rectangles. Each entity has attributes, which are its properties, like name, birth date, or roll number. These are shown as ellipses connected to the entity. Some attributes can be multi-valued, like a student having multiple phone numbers. These are shown using double ellipses. We can also break down attributes further. For example, name might be split into first name and last name. This visual structure helps us clearly define what data we're storing and how it's organized. SQL stands for Structured Query Language. SQL is the standard language used to manage and manipulate relational databases, including tasks like querying, updating, and managing data. SQL. SQL is a database computer language designed for the retrieval and management of data in a relational database. SQL stands for Structured Query Language. SQL is the standard language for relational database system. All the relational database management systems RDBMS like MySQL, MS Access, Oracle, Sybase, Informix, Postgres and SQL Server use SQL as their standard database language. MySQL command line. The MySQL command line interface allows users to interact with the MySQL database server by executing SQL statements and administrative commands directly from the terminal. Next slide cover basic operations you can perform in MySQL via MySQL command line. Query languages and MySQL basics. Let's talk about the languages used to interact with databases. SQL, or Structured Query Language, is the standard for querying and managing relational databases. SQL is Oracle's extension for procedural programming. TSQL is Microsoft SQL Server's version, also supporting procedural logic. PGSQL is used in PostgreSQL for advanced scripting. For NoSQL databases, we use different languages: MQL for MongoDB, CQL for Cassandra, Gremlin for graph databases like Apache Tinkerpop. Now, let's look at basic MySQL commands. To connect, to create a database, to create a table, use with column definitions. To insert data, to retrieve data, to update or delete, use and with conditions. And to remove a table or database, use or. These commands form the foundation of working with MySQL and relational databases. What are constraints? In a database, constraints are rules enforced on data columns to ensure data integrity and accuracy. They help maintain the quality of information in the database by restricting the type of data that can be inserted into a table. Here are some common types of constraints. The primary key. This ensures that each row in a table has a unique identifier. No two rows can have the same primary key, and it can't be null. Next, the foreign key. This establishes a relationship between two tables, linking a column in one table to the primary key of another. It helps maintain referential integrity, meaning the data stays consistent across related tables. And the unique constraint. This ensures that all values in a column are distinct, no duplicates allowed. Unlike the primary key, a unique column can contain a null value, but only once. Let's go over some essential SQL constraints that help enforce rules on the data in your tables. Primary key. Ensures each row has a unique identifier. It can't be null or duplicated. Foreign key. Links two tables together, maintaining referential integrity between related data. Unique. Makes sure all values in a column are distinct, no duplicates allowed. Not null. Prevents a column from having null values. Every row must include a value. Check. Validates that values meet a specific condition, like age must be greater than 0. Default. Automatically assigns a value if none is provided during data entry. For example, to create a table with a primary key, you can also add a primary key. These constraints help keep your data accurate, consistent, and meaningful. Take a closer look at the foreign key constraint in SQL. A foreign key creates a link between two tables, ensuring referential integrity, meaning the data in one table corresponds to valid entries in another. For example, we might have a table with A as its primary key. Then, in the table, we include a column as a foreign key that references the table. This ensures that every enrollment record points to a valid student and course, keeping our data consistent and connected. Look at two important SQL constraints, unique and not null. The unique constraint ensures that all values in a column are distinct, no duplicates allowed. For example, in an employee table, we might want every email address to be unique. The not null constraint makes sure that a column cannot contain null values. Every row must have a value in that field. These constraints help maintain data integrity and reliability in your database. Two more important SQL constraints, check and default. The check constraint ensures that values in a column meet a specific condition. For example, in a product table, we might want to make sure that stock levels are never negative. The default constraint provides a value automatically when none is specified. For example, in a user table, we might want the CREATEDAT timestamp to default to the current time. Thank you for your attention. To be continued. The lecture isn't over. Part 2 will arrive soon.